In this video, we're solving the integral of 1 over x squared minus 4x by using a trig substitution. Now, I do want to point out before we start that partial fractions decomposition is definitely the most natural method for this integral, but we already did it that way. So now we're going to do it with a trig substitution and just compare to that old answer to make sure it checks out. So as trig substitutions go, this one is fairly challenging. And the reason why is that we need to start by completing the square. So I have this quadratic term and I have this linear term, but I need to get all the variables wrapped up into a single squared binomial, and then we'll fit to the form of a trig identity. So we'll just start by completing the square on this thing. So the whole idea with completing the square is that I want to represent all these variable pieces in a single squared binomial, so I can quickly guess what that is. If I square x minus 2, that's going to give me x squared minus 4x plus 4. So it takes care of all those variable pieces. The side effect of making that transformation, though, is the plus 4 at the end, and I have to compensate for that by subtracting 4. So now we've completed the square, and I have this expression that looks like a variable thing squared minus a constant, and I have to think of which Pythagorean trig identity does this match. And we remember that 1 plus tangent squared theta is secant squared theta, and this means tangent squared theta is secant squared theta minus 1. So I have a squared variable thing minus a constant. So this is going to fit the form of our denominator. So what I'm going to do is replace x minus 2 with 2 times the secant of theta. And the reason I did that is because now if I square x minus 2, I get a 4 out in front of the secant squared. Then we can factor that out of the entire denominator. We also have to transform the differential here. So when we take the differential of the left-hand side, we get dx. And then on the right-hand side, we're going to get 2 times secant theta tangent theta d theta. So now we can transform our integral entirely in terms of theta. In our numerator, we have 2 secant theta tangent theta d theta. And in our denominator, when we take x minus 2 and we square it, again, we get 4 secant squared theta. And then we have this minus 4 hanging around. So now we can factor a 4 out of the denominator, and at the same time, I'm going to cancel this 2 up in the numerator. That leaves us with a 1/2 out in front of the entire integral. And again, that numerator is secant theta tangent theta d theta. And then in my denominator, I'm going to have a secant squared theta minus 1, and this is where we use our trig identity. That can be replaced with tangent squared theta. Now one of the tangents is going to cancel out. And then I'd like to express this in terms of sines and cosines to see what's going on here. So secant theta is 1 over cosine, tangent theta is sine over cosine. If I multiply it by the reciprocal of that denominator, I get cosine over sine. So again, this is just because I multiplied by the reciprocal of the tangent function. There's our secant theta, that's a cosine in the denominator, and then we have another sine in the denominator. So our cosines are going to cancel out, and things start to get pretty simple here. I just have to integrate 1 over the sine of theta, which is cosecant theta, d theta. Now remember, this integrates to negative of the natural log absolute value cosecant theta plus cotangent theta plus an arbitrary constant. Now that's not the only way to write that formula. As is typical with trig functions, different books will simplify it in different ways, but that's the one I happen to remember. Okay, so now we have to get our answer back in terms of x. So we need to express theta as a function of x. So if I go back to our original substitution, x minus 2 is 2 secant theta. I need to divide both sides of that by 2 and then invert the secant function. So theta is going to be the inverse secant. In other words, the angle whose secant is x minus 2 divided by 2. So now we find ourselves computing trig functions of an inverse trig function. I have the cosecant of the angle whose secant is x minus 2 over 2. And I have the cotangent of the angle whose secant is x minus 2 over 2. And of course our plus c is still hanging around. So now we have to compute these trig functions of inverse trig functions. And I want to point out real quick that the data type makes sense here. When I see a secant inverse, I read that as the angle whose secant is. So what we're doing is computing a cosecant of an angle, so that all makes sense. Now, whenever you end up with a trig function of an inverse trig function, you'll be able to reduce this into an algebraic expression in terms of x. And my favorite way to do this is by drawing a right triangle and then visualizing the angle whose secant is x minus 2 over 2. So we've brought in a picture of a right triangle now, and I'm going to put my angle right here. Now that actually is the angle theta. If I go back to how theta was defined, that's the angle whose secant is x minus 2 over 2. So secant is 1 over cosine, in other words, hypotenuse over adjacent. And the simplest way to make this the angle whose secant is x minus 2 over 2 is if we replace the hypotenuse with an x minus 2 and the adjacent side with a 2. So now I am looking at the angle whose secant is x minus 2 over 2. So to compute these other trig functions of this angle, I've got to figure out what the opposite side of this triangle is. And with a little bit of practice, this really becomes a guess and check process. I'm just trying to satisfy the Pythagorean theorem here. And that opposite side is going to be the square root of x minus 2 all squared minus 4. And we can check real quick. If we square the 2 and we add it to the square of this opposite side, the 4's are going to cancel out. And I end up with the square of the hypotenuse, so the Pythagorean theorem is satisfied. Now, if you're not seeing how to make this guess, you can always give a name to this opposite side. I normally just use a question mark for that. And then I express the Pythagorean theorem like 2 squared plus question mark squared is equal to x minus 2 quantity squared. And we solve for the question mark. Well, I do that by subtracting 4 from both sides and then square rooting the result, and we get to the same place. Okay, so now we're ready to compute the cosecant of this angle and the cotangent of this angle. So cosecant is the reciprocal of the sine function. In other words, it's going to be hypotenuse divided by opposite side. So here's our algebraic expression in terms of x, now that we've reduced this trig function of an inverse trig function. And I want to point out that opposite side, if I go ahead and expand that squared binomial and then subtract the 4 from it, I end up with this square root of x squared minus 4x in the denominator. Now we have to get the cotangent of the angle whose secant is x minus 2 over 2. And cotangent is adjacent over opposite. So I end up with a 2 over that same denominator, square root of x squared minus 4x. And our plus c is still hanging around. So we notice we already have a common denominator here. So we can just add the numerators together. And what happens is the negative 2 and the positive 2 cancel out. So I end up with a negative 1/2 natural log of the absolute value of x over the square root of x squared minus 4x. Now that's a fine way to leave the answer, but I did want to check for agreement with our partial fractions approach to the problem. And that means we have to apply some log properties to manipulate this and kind of clean it up a little bit. So first, the natural log of a quotient is the difference of the natural logs. I'm going to go ahead and distribute the negative 1/2 while I'm working here. So I end up with a negative 1/2 natural log absolute value x, and then a plus 1/2 because we took the difference of two logs. So a plus 1/2 natural log of the square root of x squared minus 4x. Now that square root can be expressed as a fractional exponent of 1/2, and then we can use the power property of natural logs to bring that out in front as a factor. That's going to give us a 1/4 out there. So what's left in the argument of the log function there is x squared minus 4x, but I want to factor that. And I'm going to write it as x times x minus 4. So now I can use log properties again and write the natural log of x times x minus 4 as a sum of two logs. And I'll go ahead and distribute the 1/4 over those two logs as I go. Oh, I forgot my plus c in that line. So I get a negative 1/2 natural log absolute value x plus 1/4 natural log absolute value x plus 1/4 natural log absolute value x minus 4. So finally, I can combine these like terms. I have a like term of natural log absolute value x. And when I take negative 1/2 of those and positive 1/4, I end up with negative 1/4 times natural log absolute value x. So I'm going to go ahead and write the positive term first. That's 1/4 natural log absolute value x minus 4. And then the negative term, 1/4 natural log absolute value x. And don't forget the additive arbitrary constant there, plus c. So now the result of this integral looks exactly like the form we got by using partial fractions decomposition. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.